Assalamualaikum and a very good morning or afternoon to the panel members and everyone present. So my name is Muhammad Aqil Danial bin Zamzuri. My student ID is 2023436776 and I'm from FSKM, UiTM Shah Alam. So today I will be presenting my final year project that is titled VulDetect, Rule-Based SQL Injection and Cross-Site Scripting Vulnerability Assessment System for Web Application. So basically, my final year project was supervised by Dr. Noor Azimah Binti Khalid. Okay, so before I begin, let me give you a quick overview of what I will be covering today. I will start with the problem statement, followed by the research objectives and scope, and then I will explain the methodology, system architecture, and also the detection rules. And after that, I will walk you through the flowcharts, the technology stack, and a live demonstration of the system. Finally, I will be present the analysis of my results and wrap up with the conclusion. Okay, so why did I choose this project? So there are three keys problem that motivated of my work. So firstly, the web applications are increasingly targeted by cyber attacks, and SQL injection and cross-site scripting consistently rank among the most critical threats in the OWASP top 10. So there are two vulnerabilities alone account for a significant portion of web security breaches worldwide. So secondly, manual vulnerability testing is labor intensive, error prone, and time consuming. During the period that testers are manually inspecting a web application, it remains exposed and vulnerable to real attacks. And lastly, there is a clear need of an automated, transparent, and evidence-based system to detect SQL injection and cross-site scripting vulnerabilities using rule-based approach, one that can reduce the window of exposure and give developers actionable findings. So based on all these problems, so I defined three research objectives of this project. So for the RO1, basically research objective one, to design an efficient system that automates vulnerability scanning and produces remediation output so that developers not only knowing what is wrong, but also know how to fix it. So the second one, RO2, to develop a rule-based system specifically for detecting SQL injection and cross-site scripting vulnerabilities in web applications. I chose a rule-based approach because it offers transparency and interoperability. So every detection can be traced back to a specific rule and payload. So for the last one, RO3 is to evaluate the system functionality, performance, and usability through structured testing. Okay, let's move on to the scope of this project. In terms of scope, this project focused on specifically on SQL injection and cross-site scripting vulnerabilities only, as they are the most prevalent and impactful web application threats. The system uses 8 detection rules with a total of 70 payloads, 5 rules with 35 payloads for SQL injection, and 3 rules with 35 payloads for cross-site scripting. So all findings are evidence-based, meaning every detected vulnerability comes with a specific payload that triggered it and corresponding remediation recommendation. So additionally, the system is able to generate a PDF report summarizing all the findings which users can download and share with the developers or stakeholders. Okay, for the methodology, basically I followed a four-phase waterfall method development approach. So basically, the first one is planning, the second one is to design, the third one is to develop, and the fourth one, the last one is to test. Okay, so let's go one by one. So for phase one, for planning and requirements, we identified the project scope, defined functional and non-functional requirement, conducted a literature review on existing SQL injection and cross-site scripting detection techniques. So for the phase two, is design. So where I designed the three-tier system architecture, defined the 8 detection rules along with their payload sets, and created the UI, wireframes, and database schema. So for the third phase was development. Here I implemented the Flash backend, built the scanning engine using Selenium WebDriver for browser-based interaction, integrated Firebase authentication and Cloud Firestore for user management and data storage, and developed the front-end interface. So for the last one is to test, where I conducted 11 test cases across functional, performance, and usability categories and performed a multi-target experiment on 3 web applications. Let's move on to my system architecture. So this slide shows the overall system architecture of VulDetect, which is my product. So the flow begins with the user accessing the system through their browser. They are first authenticated using Firebase authorization to ensure only authorized user can perform scans. Once authenticated, the request is handled by the Flash server, which serves as the application backend. When the user submits a target URL, the Flash server dispatches the scan request. And then the system then uses a Selenium WebDriver to interact with the target web application, navigating pages, injecting payloads into input fields and URL parameters, and capturing the responses just like a real browser would. And then the responses are then analyzed by the rule-based engine, which applies to all the 8 detection rules. If a vulnerability is detected, the finding is recorded with its rule ID, severity, confidence level, and evidence. After detection, the system performs risk scoring and generates a report. All scan results are then saved to Cloud Firestore, linked to the user's account for future reference. Okay, let's move on to the most important part of my project, that is the detection rules. So now let me explain the detection rules in detail. So starting with SQL injection, I implemented 5 rules with 35 payloads. So the first rule is tautology. So the system injects payloads like or 1 equals to 1 and checks whether the response contains SQL error messages such as keywords, or if the response size differs from the baseline by more than 30%. So the second rule is error based. So the system looks for known SQL error fingerprints from databases like MySQL, MySQL, Oracle, and PostgreSQL in the server response. So the third rule is union. So the system injects union select statements with marker strings like injected or pawn and check if those markers appear in the response. So the fourth rule is Boolean blind. So the system compares the response from a true condition such as n 1 equal to 1 with a false condition like n 1 equal to 2. If the responses differ by more than 50 bytes, so it indicates a potential blind SQL injection. So the last rule for SQL injection is time blind. So the system injects sleep-based payloads and measures whether the response is delayed by 4 seconds or more, which would indicate the database executed the injected sleep command. Okay, let's move on to cross-site scripting detection rules. So I implemented 3 rules with 35 payloads. So the first rule is alert pop-up. The system submits cross-site scripting payloads containing JavaScript alert functions and uses Selenium to detect whether an alert box actually executes in the browser. So this is important because it confirms the true JavaScript execution, not just the presence of the payload in the source code. So the second rule is HTML injection. The system checks whether the payload markers appears unescaped in the rendered page source. So if the input is reflected without proper sanitization, it indicates the application is vulnerable to reflected cross-site scripting. So the last one is stored XSS, basically stored cross-site scripting. After submitting the payload, the system reloads the page and will check whether the alert still fires or the payload markers persist. If it does, this confirms that the payload has been stored on the server and will affect all the future visitors, which is the most dangerous type of cross-site scripting. Okay, let's move on to the flowchart. So this is for the overall system flow. So this flowchart shows the end-to-end workflow of VulDetect. So the process starts when the user sign up or log in, then enters the target URL and submits the scan. So the system first fetches a baseline response from the target. This baseline is used later for comparison, particularly by the tautology rule. So next, the system injects all 70 payloads and analyzes the responses using the 8 detection rules. So 5 for SQL injection and 3 for cross-site scripting. If a vulnerability is detected, the system records the finding with its rule ID, severity level, confidence score, and evidence. It then maps each finding to a remediation recommendation. After all rules have been applied, the system calculates an overall risk score, display the results to the user, save them to Cloud Firestore, and give the user the option to export a PDF report. Okay, this flowchart dives deeper into how the rule engine operates internally. So when the engine receives a target URL, it first perform a reachability check. If the target cannot be reached, an error is returned immediately. So if the target is reachable, the system fetches the baseline HTML, This is used by the tautology rule for size comparison. Then it loads all the safety payloads from the rules configuration files and group them by detection method. So the engine then applies the six browser-based rules using Selenium, then include the three process scripting rules and three of the SQL injection rule that need browser interaction. After those complete, Selenium is closed and then remaining two HTTP only rules, Boolean blind and time blind, are applied. So all findings are then combined, deduplicated by a rule ID and pass the consolidation phase. Okay, let's dive deeper into the rule engine. So this flowchart shows the phase one of the rule engine in more detail. So after receiving the URL and group rules, the system starts a headless Chrome browser via Selenium. It then runs all six browser-based rules in parallel branches: alert pop-up, HTML injections, start cross-site scripting and cross-site scripting detection, error-based, tautology, and union for SQL injection detection. So each rule has its own detection logic. For example, alert pop-up check if a JavaScript alert fires, while tautology checks for SQL errors or a 30% size difference from the baseline. So when the condition is met, the finding is recorded. So once all browser-based rules are complete, the headless Chrome is closed and then the engine proceeds to phase 2. Okay, so basically this is the phase 2. So phase 2 handles the two HTTP only rules that do not require a browser. So first, the Boolean blind rules send the true and false condition payloads and compares the response sizes. If the size difference exceeds 50 bytes, all the five Boolean blind payloads are flagged. So then the time blind rule sends sleep-based payloads and measures the response delay. If the delay is 4 seconds and more, the finding is recorded. So after both phases are complete, the engine attaches the severity, confidence, evidence, and remediation metadata to each finding. So and return all findings to the main scanning process. Okay, this final flowchart shows the consolidation and scoring process. So the system receives the combined finding list from both SQL injection and cross-site scripting detection phases. It first deduplicates by rule ID to remove any duplicate triggers. Then the rescoring algorithm runs. For each finding, it calculates a contribution score by multiplying the severity weight by the confidence percentage. All contributions are summed into a raw score, which is then normalized to a scale of 0 to 100. So the normalized score is mapped to a risk level. There are none, low, medium, high, or critical. So based on all the predefined threshold. So the system then builds the result object containing the URL, status, finding, risk score, and statistic. The results are rendered on the result page with severity badges, evidence details, and prevention recommendation, that is the remediation. So user can download a PDF report and then scan the document. It's saved to Cloud Firestore with the user's ID, and there's a timestamp. So here is the technology stack used to build VulDetect. So Python is the main programming language, and then we got Selenium. WebDriver automates browser interaction for payload injection and response capture. And then we got Flask that serves as the lightweight web framework for the backend. And then we got Google Chrome runs in the headless mode as the browser engine. And then Firebase provide authentication and Cloud Firestore for the database. And then we got the client-side PDF report generation. Okay, let's continue with the system demonstration by me. Okay, let's continue to my demonstration of my project. So basically for my project, there are two 50 scan here. So this is the big file. Then we got the two small file and a front end. So for the back end, we got app.py. So this is the main Flask application that handles all routing, login, sign up, scanner, history, and logout. And then we got scanner. So this is the core scanning module that performs the actual vulnerability detection. And then we got rules engine. For rules engine is to load and manage all the safety payloads and calculates all the risks. And then we got rules.json. This is the dataset. This is the dataset where there are safety payloads of SQL injection and cross-site scripting. So here we got ID, name, category, subtype, severity, confidence, payload, description, detection method, and remediation. Okay, so continue. We got, so this is next history store. This is to handle saving and retrieving scan result from file store. Okay, then with the back end, let's come to the front end. So for the front end, here we got all the pages. So basically this is the history pages, this is the index, login, result, and sign up. Okay, so that's all. Okay, so I'm gonna continue with my actual demonstration of my project. So basically, here's my project, VulDetect. It's here, protect your system with VulDetect. And then, so here in the login page. So the first one, we got to enter your email and enter your password for users. And then, if you don't have you don't have an account, you can create one here. So basically, let's test it out. So basically, to enter email. So basically, we test. So here, enter FFF and FFF. So you can. So you have to include the ad in the email address. So okay, gmail.com. And then for password, we stay with FF. So as you can see here, password must be at least 8 characters long. Password minimum 8 characters, including a letter and a number. So what happen if we don't include the number? So but have 8, 1, 2, 3, 4, 5, 6, 7, 8. This is all letters. So must contain at least one number. So here, so we have input F 8 times. 2, 3, 4, 5, 6, 7, 8. Then we put numbers 1. Then we create an account. So account created successfully. So let's log in. So I'll use the testing. I have all the data inside it. Okay, so that's all for the login. Okay, so after the login, I'll start with my let me start with the 4 functional test cases. So I'll scan a known vulnerable target. So that is demo.testfire.net. Okay, and then which is the intentionally vulnerable for testing purposes. Okay, so for the first one, let us see here in the terminal. So here for the test case one, we got the baseline captured. So this is pass. Okay, so this is the result, the scan. So here we continue to functional testing of FT03 and FT04. As you can see here, it's all cross-site scripting only detected. So we get to see here, we also have cross-site scripting. They are currently distinguished by their subtypes. You can see here we got rule ID, vulnerability, severity, confidence, payload, what is the payload given, evidence, and the remediation. So see here, for example, for the first one, this is triggered, so the severity is high, is the basic script alert. So the remediation is apply context aware output encoding. Use CSP, content security policy. Okay, and then let's see the FT04 that is remediation mapping. So as we can see here, all is different. Yeah. So basically we plan FT01, FT03, and FT04. FT02 is basically SQL injection, as we can see in the history. Because the scan is kind of long. So let's see here. Okay, here is the example. So in this result, you can see we tested the zero web security. So basically here we got one SSS and then all the others is SQL injection. So for functional testing 02, we got to test the SQL injection scan. So here we have, for example, we got the same. So result, but in the SQL injection. So this is classic autology injection. Got the payload, and then remediation is the use parameter queries. So for the mapping, also pass. So let's continue with the performance testing. So for the first one, we got to test the example.com. So here, so basically this site has no form or input fields. So this can supposedly to approximate in about 9 to 10 seconds with a risk level of 9 and 0 finding. So this is the expectation. Wow. So let's see here. So basically, so no vulnerabilities detected. So this is expected. A static page with no input field means the detection rule have nothing to test. Okay. So let's continue to our second. So for the second one basically test for a complex target with forms and with forms and with form and input field. So basically it will longer. So here we can see it took about 62.2, and then there are results here. So this is showing that the PT02 is successfully. Okay, and then for the next one, we have to do repeatability of result and scan duration. So this one is in my analysis, so you can refer it back there. Okay, so then with the performance testing. Okay, finally, let me cover the four usability test cases. So these test cases are to assess whether a user can operate VulDetect and understand its output without difficulty. So throughout this entire demonstration, you have seen the complete workflow from opening the app into the history page. All visible without scrolling on the standard display, so no external documentation was needed at any point. So this confirmed that the test is passed. And then clarity of finding, get to see here, all are very clear and readable. So, and then we have to see the clarity of evidence. So the evidence, we have to, in each field, shows that the triggered detection, so the match is SQL injection or process scripting, uh, error fragment for ni. So the alert types captured and alert pop-up findings. Users can verify each finding themselves rather than trusting the scanner blindly. Okay, so this confirm the test VT03 is passed. So the last one is for clarity of the remediation. So let's see here, each remediation is written in plain language that a developer or system administrator can act on immediately. So SQL injection, find the recommend, parameterize queries, for process scripting, recommended output encoding, and CSP. So each recommendation is specific to the vulnerability type and is not generic. So before I forget, so you can see here, uh, each scan, we can generate the PDF. So just click the download PDF button, and then this is the result. So basically, this is the full result of scan summary. Okay. Uh, so all that is a single scan only. So we have to test because I can add URL up to 5 URL. So we have to test. That is gonna be more than one URL. So basically we have to test demo and example.com. So we have to test. So this took about a minute. Okay, so this is the result. So basically, this is the result of testing more than one URL. So here we got http demo.testfire.net. At the bottom one, we got the http example.com. So basically, we can scan up to five in the same time. So and the result will be combined together. So as you can see here, so this one for demo testfire, and then for example. Okay. So now let me show you the back end of my system. So basically, here we got two. We got Firebase authentication and also Firestore database. So basically, where's the all the data going? So this is the database. So here we got the Firebase authentication. So in Firebase authentication, you can see the registered user. So each user has unique ID. So this is the unique ID and their email addresses and the account creation date. So you so this is the database for the user authentication. So and then we got to do the Firestore. Okay, so this is Firestore. The scan, all the scan results are stored in the scan collection. So each document represents one base scan. So as you can see here, we got the results. So this is the data that has been saved. So also here we can see the user. So we have um, five account already. We have created this. We created before FFF. You can see here. Then that's all for the database. Okay, finally, let's move on to analysis. So basically, I tested the VulDetect against three web applications in a multi-target experiment. So the first target was demo.testfire.net, a vulnerable banking application. So VulDetect detected 28 cross-site scripting findings and 0 SQL injection findings, giving it a risk score of 100 and a critical risk level. The scan is completed in about 55 seconds. So the second target was 0.webappsecurity.com, another intentionally vulnerable application. So here, the system found 10 SQL injection findings and 1 cross-site scripting finding, totaling of 11 vulnerabilities with a risk score of 100 also a critical. So this scan took about 400 seconds due to the larger number of input points. So the third target was example.com. Used as a clean control site, the system returned 0 SQL injection findings and 0 cross-site scripting finding, a risk score of 0, and a risk level of none. So this confirmed that VulDetect produces 0 false positive of a non-vulnerable site. So the bar chart on the right visualize these findings per target, so clearly showing the contrast between vulnerable application and the clean control. So let's move on to the second analysis. So this is the per rule breakdown. So this slide breaks down the findings by individual detection rule across the vulnerable targets. So for SQL injection, tautology was the most effective with 9 finding. Union contributed 1 finding, while error-based, boolean blind, and time-blended return 0, which is expected since this target may not expose those specific vulnerability patterns. So for cross-site scripting rules, start cross-site scripting was the top contributing with 15 findings, followed by HTML injection with 8 and alert pop-up with 6. So in total, VulDetect detected 39 vulnerability across all rules. So the horizontal bar chart visualizes the per rule contribution, as you can see there, and then showing that the start cross-site scripting and tautology-based SQL injection were the most triggered rules in this experiment. So, all in all, to conclude, VulDetect successfully met all the three research objectives. So, the rule-based approach proved to be a practical, transparent, and evidence-based method for detecting SQL injection and cross-site scripting vulnerabilities. So, the system detected 39 vulnerabilities across two intentionally vulnerable web applications while producing zero false positive on the clean control side. So that all 11 test cases across functional performance and usability testing passed, confirming the system is reliable, efficient, and user-friendly. So VulDetect demonstrate that a rule-based scanner is scalable and interpretable alternative to traditional manual testing for web application security assessment. So that all concludes my presentation. So thank you for your time and your attention.